electric field of a line of charge. Imagine having a wire, a finite wire, this blue wire. And imagine that the wire has overall distributed uniformly a charge Q. And the charge density lambda is equal to Q divided by the entire length L of the wire. Now, I want to ask myself, at the point P, located, let's say for example, just where the half of the wire is placed, a little bit farther on the right in my picture. Because all this wire is all positively charged, let's say that the charge on it is positive. What is B? What is going to be the electric field? So I'm asking myself, what is the direction and the magnitude of the electric field at the point P because of the presence of the wire? Let me add the axis. I want to place this wire on the y-axis and the point P right on my x-axis. So the wire is now like cut in half. Half of the wire will be above the x-axis and the other half below the x-axis. Let me say that the wire goes from A to negative A down on the bottom along the vertical axis. What is the electric field at the point P? Electric field in vector form is equal to K times the magnitude of the charge Q divided by the distance from the source to the point squared times r hat. Now let's see how we can use this formula for the specific case of a line of charge. Let us isolate on the line of charge a tiny element of charge dq. I cannot use the charge q, but I can use an infinitesimal amount dq. And therefore, my equation, if it has as a source an infinitesimal amount dq, will give me an infinitesimal electric field vector dE. If I connect the charge dq with the point P, and because dq is positive, I will have that this dotted line is the distance r, and the vector here is the infinitesimal dE vector, forming, let's say, an angle theta with the x-axis. Now, let me take a symmetric below the x-axis dq, again, a tiny infinitesimal amount of wire dl, amount of length of the wire dl, where I am placing a small amount of charge dq. And then let me connect the charge dq with the point P and draw the electric field vector that is pointing away from the source. This is my dE. If you move this infinitesimal charge dq all along the half of the wire and along the other half of the wire, you will have many vectors all pointing away, and all, let's say, with this little characteristic that the y component of all these vectors, if you add them all together, will give you 0, because symmetry reasons, they will cancel up. So we are left with overall a dE that will be pointing along the x direction. And in particular, if you look at the component of the vector dE above the x-axis and the vector dE below the x-axis, you see that you have a double dE times the cosine of the angle theta. If I want to find the E net, therefore, I will have to start from this 2 times dE cosine theta and integrate it over the entire length of the wire, essentially, with the infinitesimal dq that is moving between the origin and the point A and between the origin and the point negative A. And overall, this will be a vector pointing along the I direction. Now let's substitute instead of dE, my dE from the formula. I will have the integral of 2 times k, then I have dq, then I do have divided by r squared, I have cosine theta, and my r hat is just simply the vector I along the x direction. Now what is the little charge dq? I know that lambda is q over L, and I can write that also as a little dq divided by the infinitesimal length of the wire, which, because my wire is on the y-axis, can be called dy. Therefore, dq is equal to lambda times dy. I will have here lambda times dy. Now, if you notice, I have an integral with y that could be a variable, r that is also different depending on the location of the y, and cosine theta, so theta, which is this angle marked in the picture that I'm also placing at this other for 3 directions here. So I want to in some way connect the y with the r with the cosine theta. So my integral becomes a little bit easier to be completed. Let me continue. I will have here the integral of 2 times k times lambda dy, I'm substitute dq, divided by r squared times cosine theta. Let me for a moment forget the I direction. We know that the vector is pointing along the I direction. Let's just work on the magnitude. So I was saying I need to connect y, r, and theta all together. Let's look at the picture. Y is the distance between the origin of the reference frame and the location of the infinitesimal charge dq. I can write that y divided by the distance to the point P is equal to the tangent of theta. If I'm looking at, in particular, this triangle that I'm going to highlight in green, let's say I have this side, this other leg, and the dotted line becomes my hypotenuse. So with this triangle, I can say that, let me make a little bit of room on this side here. I can say that y divided by the distance to the point P, allow me to just call it x, which is a fixed distance because I decide where to place P. So y over x is equal to the tangent of theta. Therefore, y is equal to x tangent of theta. And so far I'm good because I will need to know how much is my y. Precisely, actually, I need to know how much is my dy. So I will say that dy is equal to x times the derivative of the tangent, which is the cosine squared of theta in d theta. And that is a dy that I can add perfectly here. Now I will have to complete to know what is r squared. R. Let's look at the picture of my triangle. If I do r cosine theta, I obtain x. Therefore, r is equal to x divided by cosine theta. And let's now substitute r and dy into my equation, and I obtain integral of 2k lambda times x over cosine squared theta in d theta. Then I have another cosine theta to place over there. At denominator, I have x squared over cosine theta squared. And now let's simplify as much as possible. For example, I can take cosine squared and cosine squared, x and x squared, and I'm left with the integral of 2k times lambda times cosine theta d theta divided by x. Now, obviously, 2k lambda and x can be outside of the integration. So I will have 2k times lambda divided by the distance to the point P, that's not a variable, it's just a constant, a given, times the integral of cosine theta d theta. Now let's figure it out, the limit of integration. If I'm looking again at this green highlighted triangle, the angle theta, when the little infinitesimal charge dq is at the origin, is equal to 0. So therefore the lower limit of integration is 0. Let's see the upper limit. When the infinitesimal charge dq is exactly located at the point A, the angle theta has a specific value that depends now on the entire distance A and on the distance x, for example. Let's look closely and have the triangle back again here. This will be my A, this is my x. The hypotenuse is a squared plus x squared, and this specific theta as an upper limit can be obtained, for example, if I'm thinking about the sine of theta as ratio of sine of theta equals a divided by the square root of a squared plus x squared. And theta will be the arc sine of this ratio. Let's just leave a star so I don't have to write it. And let's keep working on this integration. This will be equals to 2k times lambda divided by x. The integral of cosine theta is the sine theta. And I'm going to integrate between 0 and that specific a over square root of a squared plus x squared. My integral is 2k times lambda divided by x. When I place the upper limit, I will have a over square root of a squared plus x squared. Now let's complete the electric field vector E is equal to 2k times lambda divided by the distance to the point P and the wire times a divided by the square root of a squared plus x squared. And that, in my particular picture, was pointing along the I direction. It's like I have the vertical axis y, the x-axis horizontal, the point P, and I have the wire located exactly here. And the electric field overall will be a vector pointing to the right in my picture with my configuration. Now the wire was a finite wire. Let me do one last step. If instead of a finite wire, I have an infinite wire, so my wire will continue above and below the x-axis, which means that the little tiny a will reach infinity above and negative infinity down or below. And allow me now to call the distance from the wire and the point P r, because this is the general letter that we see when we want to figure it out, how far is the point P from the wire and what is the electric field at this r distance. With this changement, the E due to an infinite wire is equal to 2k times lambda. Instead of x, I will write r. And now I have to take the limit for a that is approaching infinity. And using the L'Hopital rule, this limit is simply equals to 1. In vector form, the electric field is 2k lambda divided by r along the I direction, example in my picture. If you want, you can also substitute k as 1 over 4 pi epsilon 0, and the overall electric field in magnitude becomes, because the 2 will simplify with the 4 at the bottom, becomes lambda, the charge density distributed over the wire, divided by 2 pi epsilon 0 times r. This is in magnitude, and in direction you know that is away from the wire. Thank you.